as you can see in the title, the topics that I'm going to discuss or talk about today is graph neural networks, and this is going to be the last topic in this semester, right? So remember last time we learned how do you integrate the physics knowledge into the data-driven or into the deep neural net, and we demonstrate some the pins with some of the easiest sample examples with you guys in order to help you to understand. And here it might be it's gonna be totally different, but I pick or select this as the last architecture or topics. So I want to show you some of the graph. And I think most of you or most of them is not maybe it's the first time to heard of the graph, or most of them not familiar with that. So I want to introduce the graph neural nets. In order to that, I have to explain what the graph is. So that will be, I'm going to show you graph first. Here this. This one is, we need the materials for the concept, or you need to understand the properties of the graph in order to later on to have a better understanding of graph neural nets. So let's see what graph is. So people might say graph or networks. And pretty much these two are identical. And in many mathematical theory, or we have graph theories, or you might see a lot of engineering applications. Some of the engineering applications can utilize the concept of graph or networks. So here it said it's abstract relationships or topology and connectivities. You can think as somehow graph can utilize the concept of relationship or topology and connectivities, that kind of mathematical tool to represent the relationships or connectivities. Right? The key elements. The graph requires two key components or elements. One is V and the other one is E. The first one is sets of vertices, or we say nodes. And the other one is set of edges or link or relations. And sometimes we need to define weights. So it's related to the edge properties. And I guess this is kind of the famous examples. You're gonna see this kind of pictures whenever you see the graph. Okay. So in we have downtown or cities around, and there's some bridges or they represent some kind of connectivities. So these two are the same, and the physical, we have, or you can represent this one, you can represent it, how do I say, we have C and A and B, we have D, and we know that A and C are connected like that, and you have this kind of connectivities. Right? And this actually doesn't have to be like this. We have we have A, where's B? You have B. We can write it A, B, C, D. And see the connectivities between A and C. We have like that. Connectivities between A and B, like this. Connectivity B and D, we have A and D, we have C and D. So those are pretty much they represent the same thing. So that means it's like in a sense, in topology sense, these two are the same. And we might write it like here, 1 or 2 or 3 or 4 and 1. It can represent many things, and in this case, for example, we can give like these weights can represent the distance, right? or strength in strengths of connections in a personal networks, right? So these are either 2 or 3 key components, right, to build up the graph model. And actually there are 2 graphs. One is, the first one is directed, and the other one is going to undirected. That means we have directions. So like this. If you draw like that, that means probably no direction. So if you might have like that, so from A we can reach B, but from B we cannot. So we can represent, these arrows can represent whether the networks or the connections we might have, whether it has the directions or not. I want to show you some of the examples, like say graph models any situations where you have object and pairwise relationship. It could be symmetric or it could be asymmetric. That means this one is symmetric, that means directed, or this one is can be represented by undirected. No, I'm sorry. This one symmetric property can be represented by undirected graph, and on the other hand, asymmetric can be modeled as a directed graph. So I want to show you some of the examples here. Vertex AMS node. So like say we have like people A and B and C and D's, and if like the people like each other, that means person A and B, they like each other. And another example of say the people is a boss of the, so A is like if represented, that means A is the boss of B, things like that. And it could be the task. Say a task cannot be processed at the same time. That means, if we have like that, that means the A task should be processed before task of B. Things like that. Right? Computers, airport, cities, airport. Like if we have like this, we have airport C and airport D. If we have undirected graph, that means the planes flies between them. If you have like that, that means the plane can fly from C to D, not from D to C, things like that. So I guess with these, the examples, probably you kind of understand what graph network is. So for graph representation, let's see, the question they might have, how to represent graph for the computer to understand it. See, say this one, for example, say how many vertices do you have? 6, right? And we can draw like this, but like human beings like us, we have no difficulties of understanding. But the problem is we have to let computer know and let computer understand. That's the problem. That's the first questions or first issue that we have. That's the questions. Any guesses right here? And one way, I would say one way, I guess there are more than one, but one way that we can represent it is that graph can be represented as adjacent matrix A. Adjacent matrix A indicated adjacent node for each node. That means I will take this one as examples. We have 7. From A, we have connectivities 2, we do, and 6. We do not, right? That's one way we can represent it. Let's take this one, and 1 and 3. 1 and 3, and others are zeros. I'm gonna keep doing it on 3, let's see. 2, 4, 6, 7. You guys see what I'm trying to do? 4, 3, 7. Number 5, we have only 6. Number 5, we have only 6. Number 6, we have 1, 3, 5. 7, we have 3, 4. So that's the adjacent matrix represent the graph, right? Do you see any properties in adjacent matrix A in this case? Can you recognize or notice any properties that the adjacent matrix A has? What kind of property that? This one is, let me see. Yeah. The hint that I'm trying, it's undirected graph. That means, like, if we have from A to B, from B to A, right? There's no directions. So it's symmetric. So looking at adjacent matrix A, it's a symmetric matrix. It's a natural way, right? So undirected graph, if you represent or represent adjacent matrix of A for undirected graph, that matrix is gonna be symmetric. So that's how actually I did that. And the undirected graph, again, these are two key components, vertices and edges, and let the computer, again, to understand the structure of a graph. We have vertices from 1 to 7, and these are the edges, like here. Not say from, it's between 1 and 2, between 1 and 6, things like that. We don't have any directivities. And from let me see, that's the adjacent list is that this one is we pick node 1, and from the graph we can see that these two nodes are connected. So that's the adjacent list, and you have 2 and 6. That's how you build up the adjacent matrix of A. And again, I said it's symmetric because the model that we have is undirected. let's move on to, same structures, but in this case, I said that it's directed. That means we have like arrows like that. Okay. In this case, I want to show you. I want to set it. Let's take node 2 as an example, and adjacent 2 is equal to. Looks like these are connected, but the only adjacent is 3. Right? One is not connected because of we are not able to travel backward. And in this case, of course, it's not symmetric anymore. It's not symmetric anymore. So it's not symmetric. Okay. For directed graph from A to B, from B to A is going to be different, of course. So I want to give you a quiz, and I want you to get the adjacent matrix for the first case and adjacent matrix for the second case. I will give you like a couple of minutes to think about it. So that's how I'm trying to do. Since this one is directed from 1 to 2, 3. From this guy, this is the only one. For this guy, this is the only one. This guy, for this guy, all of them are zeros. And let's try that, the undirected graph. From 1, these two are connected, and from 2, 1, 3, connected, and 3, 1, 2, all of them. For 3, 1, 2, 4, 1, 3. And see, from 1 here. See if that matrix is a symmetric or not. You have to check. Right? It should be symmetric adjacent matrix for undirected graph case. Okay? This is going to be the answers. And the next question that I have is this a little bit difficult, but it's not that difficult. So the question is that, so the first one is that given graph, I want you to come up with the corresponding adjacent matrix. And here, actually is in vice versa. We have with this the informations. I want you to draw the corresponding directed graph. Again, I'm going to give you a couple of minutes to think about it. The reason that I wanted to showing the graph, and I wanted the touch on the graph neural net is that because if you think about the data set or input data that you might have in your near futures or for your interest, image probably like in the form of matrix or tensors, and if you have a sequential data set like vibrations, and there will be the sequential data set. And another type of data is like, how do I say, you might have data set that later on you might have to think about the graph representations. In that case, probably you can model your problems with the graph and using that graph neural net to estimate it. That's why. Okay, let's think about these problems. So we have 6 vertices. So I want to just 6. Oh, I'm not. Let me see. So we have 0, 1, 2, 3, 4, 5. And for this guy, we have, and this directed. And for this guy, 2, 2, 2, 2, 3. For 2, we have 4. 3, we have 5. 4, 4, 4, 4. Here, 3 and 5. And 5, we have nothing. So that's the graph. Okay. And thing is, actually, this is what. So what I'm trying to say is that, let's see, this one. From 0, we have 1 and 2. From 1, we have 2 and 3. 2 and 4. 3 and 5. 4, right? So these are the same. But like, if you just, at a glance, it looks different. But the graph represents only thing. This is the number of nodes and the relationships. So basically, these two are the same, or I would say identical in the sense of topology, or in the sense of connectivities, in the sense of like abstract the relationships. So this guy and this one are the same. Okay. So I'm done with definition of graph, and the key, like 2 different, one is the directed and the other one is undirected. And now from now on, I want to talk about some of the properties. So first one is degree. Degree. So that's kind of the definitions in the graph. So let's see what is the degree for undirected graph first. I want to see. So that's the, imagine you have some kind of undirected graph in your mind, and that's some. So degree of vertex. So degree is, we don't define what the degree is yet, but you might from this sentence say the degrees can be defined or assigned in each vertex. It is the number of edges connected to it. So we denote it as a degree of vertex I is d of I. So let's see, what's this? So what's the degree of vertex of 1 in this graph? What's the degree of what is this? So by definition is the number of the edges connected to it. What's d of I? How many edges are connected for this guy? 3, right? So we have 3 guys. What about d of 2? 1. D of 3. 2. 2. That's the degree in this case. Okay. And the first thing is, so this is the adjacent matrix of A, right? So how do you, so this one is, what's the relation, how do you compute the degree out from, suppose the adjacent matrix is given, how do you compute the degree? You can add up like this. Because that's the definition, right? From definition of degree, that's how we compute. So actually, for degree, like you can write it this way, or it's in this way. And let's define. So these are the definition of degree. Let's define the degree matrix. D, capital D, is that, so these are the degree, and we just create the diagonal matrix out of it. So that's the definition of degree matrix. I mean, okay, so from now on, so since we had, like, I'm introduced the definition of graph and some of the properties, and don't think about why. Just these are the definitions. So eventually we're gonna use later on, right? So don't think about why we need that kind of definitions like degrees, and don't worry about it at this moment. So so from undirected graph, I mean that means that, say, this adjacent matrix of A, and we have index of I and J. If you do summations, that's same as I. That means, I mean, in this is kind of mathematical expressions of doing like that summation in cross in this way. So from degree matrix, what we can see is that, hey, from this information, that means the first node, we know that 3 connectivities or connections. That's the information that we can extract. And let's move on to the next properties. Self-connecting edges. What is this? So I mean, don't look at, just looking at this guy. So that's, and you see the difference? Now just only the difference is actually the network graph is essentially pretty much it's same. The only thing difference is I add another connections, which is self-connected. So adding, okay. So this is the from this guy. By adding the self connections, that means starting from the node 1, we have another, self-connected. So from 1 to 1, that's exact. So we have to add 1 in diagonal. Okay. So that means that what we can do in mathematical representations, so given A matrix, like this, say this is A, if we add identity matrix, like this one represent self-connected. Edges are edited into the original graph. Okay, and here we can compute D, and I want to say this is another degree matrix, but not A. It's from A plus I. The self-connected edges included. So just doing summations in this way, that's how we got. So let me say it again. From drawing of graph, that's the only difference is that we just add like self loops for each node. And the difference between the adjacent matrix is that suppose this is original one, just add another, add identity matrix that. And for the difference for the diagonal matrix, the original was I represented D, and for self-connected I had D tildes, and the only difference we add 1 into the diagonal components. Because, for instance, for this guy we have 4 connections. 4, right there. Another either definitions or properties, I would say definition is neighborhood normalizations. Some nodes has many edges, but some don't. So for example here, some has like 4 of them and some of them has only 2 of them. You can think like this is, if that's some kind of represent like the connections between the peoples, and someone has like friends 4, including we have 4, or some of them has 2 friends. So considering neighboring node is in a normalized weight. So we want to normalize it because why? Because some of them has many edges, some of them doesn't. Do not have many of, so small number of. So somehow I want to normalize it. And another issue, so this one is the first issue. The second is to prevent, you don't have to worry about this thing, the third bullet at this moment, but have issues on the numerical instabilities and vanishing experience gradients in order for the models to converge. But at this moment, you guys don't have to worry about it. So how do you normalize it? So in this case, so for example, the first node, we have 4 of them, so I guess like we can divide it by the degree of itself. And for that guy, right, we have 3 of them, and we have 3 of them. That's one way that we can normalize it. That's one way that we can normalize. And let me see. For A, I will say it's A tildes. We have that's A tilde matrix, adjacent matrix, and we know that the tilde, the degree matrix is like 4, 2, 3, 3. Only information is located in the diagonal components. What we can do is that basically what we want to do, what we want to compute. This is not A tilde. This is A plus I matrix. I want to do neighborhood normalizations. And what I wanted to, because we know that the first node has 4 connections, so probably that's what we want to do. And 2 divide by half. That's something that, so from these two, how we compute this guy? What we can do is that, what's this guy? I want to compute the inverse of that. Usually if you have 4 by 4, it's almost impossible to compute the inverse by hands. But in this case, we have only, it's a very special case, we have only diagonal components. So in the inverse is like, things like that. So if you compute, do you need to compute like that, or what do you think to get this guy? Number 1 or number 2? It's linear algebra. I mean, you have to compute it, but say that this is the guy. To normalize it, to get neighborhood normalization matrix, or this matrix. In this case, we indicated A tilde matrix. And I mean, you have to think about it. This is the guy. So what we can do is we can define A plus I matrix as A self, and we have to compute the inverse of that, T matrix, and we need to do multiplications. So that's how we do it, and that's how we got. I mean, I don't see any difficulties and problems, issues at this up to this point, but actually there is some issues. There are some issues. So see, that one is that the original, the purpose is that, okay, here we have undirected graph, and somehow I want to add self-connected loops, and that's okay. The only thing is that what we can do in the mathematical representations or matrix calculations, just add identity matrix, which is okay. And another thing is that some node has many of them, many connections, and some do not. So I want to normalize it. That's kind of natural way that you can think of. So just since we know the informations, or we know the degree informations for each node, and we have degree matrix T, somehow we can compute things, decide to do that, and that's kind of, we can believe that, we're hoping that A tilde matrix is kind of normalized. So that's how we got. But what kind of graph that we are talking about at this one? This one has undirected graph. But look at this. Do you have any uncomfortable feelings or not? See, again, like I say, it's undirected, and this is corresponding something like adjacent matrix, but it's self-included and neighborhood normalized no matter what. But think about looking at matrix of A tilde. Since there's some representation for undirected graph, so that should be symmetric matrix, right? But look at, is that symmetric or not? It's not. So there's some kind of issue raised. So it's not symmetric. It's not symmetric. That's why I said this is first naive attempt. First naive attempt. We have to do something more, or something, we have to do something smarter to normalize it. You see what? Okay. So I'm gonna do. Okay. So let me see. So this is normalize A tildes, and the previous one was that I want to like, and this is not. So, but if you do that way, now it's symmetric. I mean, I'm gonna show you, but I'm gonna skip a lot of details. I mean, I guess some of you may like, for those who took linear algebra, like, how would I say, like S, like things like that. You might. Actually, there are so many things that we have to know and we have to discuss. The first thing is that we know that this is the D is a matrix, and how we can define this guy. Can you think about like the power to any given matrix? We can like say D matrix, like we can define that. This one is not like, this is inverse, but I'm not sure. Where is this? Power to the half of matrix. It's not intuitive. And in this case, we have. Of course, it's like definitely it's gonna different like do the power for each components. It's not. All right. So again, I'm not gonna go in details. And say this is the normalized, another second attempt. And how do you compute these guys? I don't know. So let's use just the Python. And in SciPy linear algebra, we can import a fractional matrix power. So this is matrix power, but it's fractions. And from D, fractional underbar matrix underbar power and minus half, and we will get this guy. And from A self is as we made it as a matrix, and this one again is made it as a matrix. So we do A plus I, which is, and we do D half norms and D half norms. Back and forth. That's, we got A. And if we compute it, this is what we got. Now, somehow, look at these, looks like symmetric matrix. Now, this is normalized neighborhood normalized matrix of A. Look. Now it's normalized it. Okay? So what I'm trying to say is that this is not, you should use that one for neighboring normalizations. I'm going to revisit it because we have to use that in graph neural nets. Right? That's kind of the things that I'm supposed to cover. And let me see. In Python, we have another package you can deal with networks. We call it NetworkX. And we import NetworkX and we represent it as, we shorten as NX. And this is kind of the syntax that we have. We define graph. And these we add node. And we add edges like that. And draw. Then this is how like Python's or NetworkX is able to provide for us. Of course, from the graph that we already define it in here, and actually you don't have to compute it like adjacent matrix or degree matrix. You don't have to compute it. Just type it, nx dot adjacent matrix. This is what we can get. Right? So basically what I did is that I introduced the concept of a graph and things like that, and those are the definitions and key components, and the graph might have directed or undirected, and there's how to represent it, and let the computer understand and know, and that's adjacent matrix one way they can do, and that's how explain it, adjacent matrix, and from graph, we supposed to be able to get adjacent matrix. And from the adjacent matrix and how you draw the corresponding graph, things like that. And I show some of the definitions or properties. And the first definition, first the degree for each node. And self-connected loop, how we add. Just add identity matrix. And for normalizations, and this one is not, and we're supposed to do it like this. Right. And a lot of details are skipped, and if for the advanced learners, probably you have to take a look at like linear algebra, things like that. And there's functions you can use, and all the necessary tools and functions related to graph or networks are already programmed and made it available for you as a Python package or libraries, and use NetworkX. So I'm just showing the easiest examples of how you define the graph, and it gives us the next thing is how to extract adjacent matrix, or how to extract the degree matrix, things like that. So that's kind of all the things. I mean, we have many more stuff we can talk about related to graph, but I'm gonna skip all of them, and I'm gonna move on, jump into the graph neural nets. So again, say graph. I want to show you some. I want to start with some of the motivations why ANN or CNN, RNN. I mean, you learn a lot of things, and the motivation is why we need graph neural nets as well. So characteristics of graph data. Graph is that relation. It contains the connectivities or connections or relationship between data. Okay. Suppose you have, you have many like friends or person or group of persons. Like these are the data. You can extract the features out of it. Say like first person is how old is he, what's the height, tall, or how weights, and whether it went to what kind of college or not. You have a lot of features can extract. And for example, for supervised learnings, I don't know what kind of Y that you can say this is some kind of, from these the extract features you want to estimate something. It's going to be your output. And this will be one set of data point and another pair of data points for supervised learning. But here, the thing is that by doing that, the assumption that we made or underneath is that these persons are independent of each other. Right? All the data points are independent. Using this kind of supervised learnings, I want to have another information, which is in say we have persons like from 0 to 1 to 4. We have 5 of them, and these are the connectivities between persons, between people. With all these, say this is the feature vectors, and we have feature vectors like that for all of them. And the connectivities, that's the additional information that we have. I mean, the connectivity is like has nothing to do with individuals. Right? These are the feature vectors for corresponding individual, like here is, we say personal node. And the graph representations provide additional information, which is like are connected, or let's say they know each other, or like these are relatives, whatever. I mean, no connections between them, direct connections between them. So the idea is that we want to have this dependent informations into account whenever you do some kind of predictions or build up the models, whatever. And individual features, we have that. So that's kind of the motivation of why we need to think about the graph and graph neural nets. That make sense? So for all the data points that we discussed so far, we assume that all the data points are independent. That's the assumption that we had. But starting from now on, if we have that kind of connectivity informations, we can model like dependency between the data points. How do you represent the dependencies? We can connect it. Like I said, it could be directed or could be undirected. But this one is easy for us, but not easy for computer. So in order to make the computer to understand, again, it's adjacent matrix. Now I want to make a connection between convolutional neural net and graph convolutional networks. Let me see. I want to show you some similarities between starting from convolutions. Let's see. Again, take the image as examples, and we have image like that. You can think of MNIST data set as, the first thing that we need is we flatten this guy and fit into the ANN networks. So the first network was that That's the input. And we add like hidden layers. We have the connections, all of them. That means for this guy, we trying to gather information from all of them. Like this. We made connections actually, and throughout the training process, we want to see whether this some of the has very strong relations, some of them not. So that's why we add like, it really depends. Eventually, we'll get like weights, all the weights. But the idea of CNN is that we build up like 3x3 corners. The assumption behind is that to get next layers, for this guy, in order to update the pixel values for this guy, that means that based on the convolutions operators, I will not consider it only like these 9 data points. That's the idea of, right? So that means out of it here, like I'm going to only consider it the neighborhood information or data points. That's what the figure represents, or trying to tell us. Why is that? Because from images, we kind of know that these are connected. So you can see the graph or pixels as another graph representations. So each pixel like each node, and they are connected. So image, very special case of graph. All the nodes are like in grid and connected like that. I'm not sure the connections between, but okay. Again, like I said, this is, you can see as a graph, but the structures are they have very unique structures. And I want to generalize it. How? That's kind of graph. So graph is kind of generalized or version of convolutions. So this is more generic expressions or representations. And this one is like here, regular structure. The major difference is the CNNs are very special built to operate on regular structures, graph data. Graph convolutional nets operates for the graph that the number of nodes connections varies and are unordered. So this is more generic, can handle the general expressions. Just remember, CNN is very special or specific case of GCN. So GCN is more generic, has capability of like representing more general expression, general like the structures to data set or relationships or connectivities. Okay. Let me see. Let me show you. So next thing is that I want to build up like some kind of basic component or basic idea of GCN, but I think I have to stop here because we have only 10 minutes. We have more stuff, then it's kind of difficult to stop in the middle. So okay, so I will stop here. So what I want to summarize what we did today is you might think this is totally like kind of looks totally different from what we used to do it. So I want to show or introduce the graph neural net, but because nobody, I mean, like the concept of graph is not like the familiar. So I introduced the concept of graph first, and I spent most of the time to explain it, and later part of that kind of I'm trying to see. This one is why we need that is the connections. I mean, starting from I want to show you the difference between or starting from convolutional neural net to I want to extend it or expand it to graph convolutional neural net, and that's the key point, right? And next time I will show you the basics of graph convolutional neural net in more details. All right? So with that, I will end and I'm going to stop here.